Hi. So today we are going to build a multiplexer. The way that we're going to build this multiplexer is through the use of four 4051 chips. These 4051 chips are a 1 to 8 transistor latch. You use a 3-bit address to select which switch the center common switch is connected to. So it works like an 8 to 1 switch. So if we have 0, 0, 0 selected, it goes to the very first switch and it connects the common through to the very first output. If we have 1, 1, 1 selected, it goes to the 8th one. So essentially it works just like a switch would, with just the selection of the switch being done through binary. It also has some other tricks up its sleeve, but let's talk about how I'm going to actually implement that. We have 8 digits worth of parallel data that we need to multiplex out. So this works perfectly. We need 8 sets of 4 bits representing each a BCD digit. So if we need to represent 7, for instance, then we'd have 1, 1, 1, 0. So that 1, 1, 1, 0 from least significant to the most significant in that case needs to be sent out to the display. Well, we can do this in a few ways, but with the way that we're going to implement here, each of the common lines goes to the output, because the 4051 is actually a bidirectional multiplexing switch. It can do a little bit more than that even, but we'll get to that. So we have each one of these 4051s connected up to the output on the common. So that common is here on my little, hand diagram here, and it switches between what digit we need. And there's 4 of them, so they're each selecting one of the bits. And in that way, we can select each one of the digits times 4 and get out our multiplex data. That's about it. That same digit select function here is also going to be telling the output what digit that is, because otherwise it's just nonsense data if you don't have a clock to try and extrapolate that from, and even then it's a bit iffy. But that gives the multiplexer, the display multiplexer, the information it needs to find out where to put that digit on the display. And that's about it. Let's get to it. I'll come back when it's all built up. Hi. So the prototype's all wired up. Everything's nicely loomed, in my opinion. And we can go ahead and kind of figure out how everything went down here with my handy dandy pinout. We can see that we have 4 pins in a row being the input pins for the BCD data. So we'd have the data information coming over this parallel bus here, and the data information for this part all in parallel in a row like this, with 4 bits equaling out to one of the BCD data lines, or just 4-bit binary, or really anything in pairs of 4. It's 4 times 8 to 1. So anyway, over here we have, and by the way, that's all blue on the board. Over here we have our white wires, which are our address lines for the chips. Select which 8 to 1 pin to use, and that's just a 3-bit 0 to 7 select, so it's got 8 possible states. Hence the, 1 to 8. The output common pin is these red lines here. This is what actually goes out to the display driver, and in combination with the address select, tells the display driver, or whatever it is that we're multiplexing to, what digit is actually being represented on the data payload represented out here. So in the case that we had 0, 0, 0, and we had 1, 1, 1, 1, that means we would have the full 15 out on the, or the 16th position, depending on what the data is actually doing, out on the bus, and it would be on the very first digit. That is to say, it tells exactly what digit it is. You can probably guess what it does. I went a little bit overboard with the coupling, decoupling on here, and I bodged this one on because I didn't like how far the power line had to run over there, and kind of unnecessary. Something to keep in mind is this is actually an analog demultiplexer. Now with these long wire runs, even with the nice looming, we're probably not going to get anything north of 100 kilohertz, or maybe that's optimistic. These chips are maxed out at 10 megahertz or so with a 12-volt bus on the data sheet. But these are probably fake chips. They're cheap. That doesn't mean they won't work. It just means that their dies are probably photographed and then they use bad masks, and that's a whole nother topic on its own. But I think we'd be lucky if we got a megahertz out of these chips on a good day, so let's just assume that we can get a max of 100 at any given point with this board. The way that this board interfaces is with a standard IDE connector, and I will have a indicator drawn on the back here, but it's just like that. And this bus out here can go to a recorder or a serial to parallel interface, and then this end here can go to the display. That's pretty much it. We can't do much with this until I create a board that we can be driving something with. And as a little bit of a foreshadowing for the next video, I have this lovely display soldered with, I think this is 16 gauge wire, pretty sure. And we have our outs all in parallel. Looks to be a bit of a mess, but that's what you get when you use sockets that aren't designed for PCB mount. And we have our anode select over here. So we'll drive these Nixies using this multiplexing board. And, oh, I forgot to mention, this last pin over here is the clock. And this board has no use for the clock, but the board that decides all of the digit selects and creates the address selection will need that. And we can use that same frequency to be running the high voltage supply. So that way we'll have our pulses for digit selects in phase with the demand for power on the ignition, which means far less filtering. We'll get into that next time. And we might break that up into a power supply drive line, and that might also become part of a board. I'm not sure how I'm going to do the video breakup, but that should be interesting. That's for the future, but this came out pretty good. I'm happy with this. That's about it. Hopefully I didn't forget anything.